Good morning. Today we are doing the last lesson in Module 4, Linear and Nonlinear Functions. So yes, it is a very intense unit. And this is Module 4.7, and today we are talking about absolute value functions. So let's look at our learning target. I can graph absolute value functions. I can apply translations to absolute value functions. I can apply dilations to absolute value functions, apply reflections to absolute value functions, and I can interpret constants within equations of absolute value functions. So yeah, this is a pretty long unit, but it is so connected to module 4.4. So if you have any questions on different forms of transformations, which is translations, your dilations and reflections, I would recommend that you go back to module 4.4 for in-depth lesson into all this stuff, because that's exactly what we are going to be using over here. So let's look at what an absolute value function is, okay? And this is a type of piecewise linear function, because see, we have this here and we have this here. So it's not continuous. It is like, you have two pieces in this case. So it's like a piecewise function and a linear function, and it is written, the parent function for this is f of x is equal to absolute value of x. So I know that there are two integers that are going to give me exactly the same absolute value. And absolute value is nothing but the distance of a number from 0 on the number line. So I know that 2 is the same distance from 0 like -2. Same thing if I have 8. What's the other integer, which is the same distance from 0 on the number line on the opposite side, which would be -8. So 8 and -8, 15 and -15, 2 and -2. All of these are basically the same distance from 0 on the number line, but they're on the opposite sides. So that's basically what absolute value is. So we're talking about distance, and distance is always positive. So we talk about how many units something is away from 0 on the number line. So that is why the parent function f of x is equal to absolute value of x. It looks like a V. Okay, so look. This is what it looks like. All right? And the vertex is going to be at the origin, which is 0, 0. So basically, what is my parent function? Once again, it is f of x is equal to absolute value of x, and then f of x in which x is either greater than or equal to 0, and also x is less than 0. And that's what I was saying, that you have the two values which are on opposite sides of 0, but the same distance from 0 on the number line. Okay? So now let's look at the equation for absolute value. Okay? The equation for absolute value is f of x is equal to a absolute value of x minus h plus k. So where a, h, and k, these are all constants, and f of x is greater than equal to 0 for all values of x, and the vertex here, okay, this is either the lowest point or the highest point of a function. And for the parent function, y is equal to absolute value of x. As I said, the vertex is the origin, which is 0, 0. So it's the lowest point, but it can also be the highest point if it is graphed this way. Okay, so let's look at a couple of other things here. We just said the graph is V-shaped. Okay, so as you can see, graph is V-shaped, and we know that the domain is going to be all real numbers, and the range is all non-negative real numbers. Okay? And so the vertex is always going to be the ordered pair of the constants which we are using as h and k. So look at this equation once again. So this and this, that becomes the vertex, which is the ordered pair of x and y. So when we get into that, the problems, you will understand this better. All right? So first thing, let's talk about now the different forms of translations. We're going to quickly refresh our memory before we move on to questions relating to absolute value. So let's look at our different forms of translations here once again to refresh your memory. And we know that we have vertical translations or we have horizontal translation. Okay, so let's look at this one. What do we have? The first one, if I have given you g of x is equal to absolute value of x plus k. So I'm adding that constant. So what do you think is happening to my graph? It's going to move up. Okay, so in this case, let's say I say plus 3, plus 4. It is basically moving up those many units. So when the constant is added on the outside, my graph is moving vertically up. Okay, so this one goes up. What about when I'm subtracting a constant? So minus 8. So it is moving 8 units down. So therefore, in this case, my graph is moving down. So that is my vertical translation. It's going up or it's going down, depending on whether this is plus or this is minus. Okay, let's look at the horizontal shifts. And we've talked about this before. Now look what's happening. They are grouped together inside. So that has to be performed first. So when I am doing the absolute value, when I'm subtracting, which direction does it go? In the opposite. So this graph is going to shift to the right. And if it is addition, it's going to go in the reverse. So what it's going to shift to the left. So these are the different types of translations that we need to first remember. So once again, if k is greater than 0, the graph of f of x is equal to absolute value of x is going to be translated k units up. Okay, and in the other one, if it's less than 0, it's going to be translated so many units down. And that's what we just discussed. If it is minus, if it's now grouped and we have the horizontal, if h is greater than 0, the graph of f of x is translated, h units right. Okay, so, and if it is less than 0, it's going to be translated so many units left. And so this is basically a review of what we have done with translations. So, let's look at this question now. And it's talking about vertical translations of absolute value functions. So, it's saying describe the translation in g of x is equal to absolute value of x minus 3 as it relates to the graph of the parent function. So as you can see, the constant is on the outside. So we know this is going to be a vertical translation. And since it's a number which is less than 0, all right, so it is minus 3. So this graph is going to be moving 3 down. It's going to be translated 3 units down. So let me show you the graph really quick. So look, my parent function is 0, 0. That's where the vertex of the absolute value function is. And so now we're going to take that vertex and it said minus 3. So we are going 1, 2, 3 down. And everything is moving 3 down. And so it is moving vertically. Okay, and now, so therefore, let's go ahead and talk about another one. And let's say, so we have over here, this has moved how many units down? This is 3 units down. And this is where we have the new vertex. And everything over here, it's 3, look, 3 units, whichever way you go. This graph has moved 3 units down. Okay, so once again, it is a translation of the graph of the parent function, 3 units down. Now, let's look at one. And we have this graph over here. And we're going to describe this translation. Now, we can see it's saying describe the translation, and in j of x is equal to absolute value of x minus 4 as it relates to the parent function. So now we know the parent function, the vertex is at 0, 0, okay, which is over here. Now it's saying x minus 4. So now think of what we've learned. If it's saying x minus 4, it is moving to the right, not the left. Because of the minus, it is moving 4 units to the right. So look, 1, 2, 3, 4. Here we go. So this graph has shifted 4 units to the right. And this is going to be a horizontal translation. Okay, so it's going to be this is a horizontal because it's moving, it's shifting left to right. The other one was a vertical one. This is a horizontal translation, okay, because it is shifting right or left. But since it's x minus 4 absolute value, it is going to move to the right 4 units. So translation of the graph of the parent function is 4 units to the right. Now, let's do one where we have multiple translations of absolute value functions. So, let's do this one. Okay, now we have multiple ones over here. Okay, that means we can have vertical and we can have horizontal at the same one. Okay, in the same function. So, let's look at this one. It is saying describe the translation in g of x is equal to absolute value of x minus 2 and then plus 3. Okay, so this part is telling me that this is a horizontal shift or horizontal translation, and this part is telling me that this is vertical. All right, so we have 2 of them going on. So when I say the parent function, we know this is 0, 0. Here's my vertex. And if it's saying x minus 2, what's on the opposite of minus? That means we are going to move to the right. Okay, so this means I am moving to the right. So I'm shifting to the right, and that is why that is a horizontal translation. And then it's saying plus 3, so I am going to move up 3 from there. So now let's do that. We are going to shift from 0, 1, 2, and that's how much we said to the right. So this is 2, right? And then it says we are moving up 3. So 1, 2, 3. So look, here is my new vertex. Okay, so again, the equation has both the h and the k values. Okay, and so if I have both the h and the k values, what am I doing? The input and output will be affected by the constants. And so the graph of f of x is vertically and horizontally translated. And so once again, it's the translation of the graph of the parent function, 2 units to the right and 3 units up. So now what we're doing is we are going to use the graph that is provided to us of the absolute value function, and we are going to write an equation for it. So first thing, please remember, you need to see whether the graph is shifting right or left, and so it's horizontal shift, and then if it is moving up or down, which is a vertical translation. So the equation for an absolute value function is f of x is equal to a absolute value of x minus h plus k. So please remember, a, h, and k are the constants. So let's look at this graph. This is the blue is my parent function, which is here. Okay. So my origin, my vertex is at 0, 0 for the parent function. Now let's see how much has it moved. Okay, I can see that this is a horizontal shift. It has moved 1 unit to here, 1 unit to the right. So if I'm moving to the right and I'm writing an equation for this, this is g of x is equal to, let's look at this. If it's moving to the right, what am I doing? Am I adding or am I subtracting? I'm definitely subtracting. So I'm doing the x, and then we see minus. If it's minus, then it moves to the right. Remember, that's the shift. So how much has it moved? It has moved 1. And so my equation for this other, for this function is going to be g of x is equal to absolute value of x minus 1, because the vertex is 1 unit to the right of the origin. Okay, so and that's how I write my equation. Let's try another one. So let's look at this one, and we're identifying the absolute value functions, and we have multiple translations going on over here, and we are using the graph of the function to write its equation. Okay, so we know that the equation has to be in the format of f of x is equal to a absolute value of x minus h plus k, and the vertex is the constants over there. The h is my x value and k is my y value for the vertex. And so that's why I've written that ordered pair like this, so that you know this h is x and this is y. All right, so let's look at this. Now we can see that the graph has shifted 2 units to the left, and it has moved down 1, 2, 3, 4, 5 units. So look, it has shifted 2 units to the left, and it has shifted down. So this is 2 left and 5 down. Okay, so when that happens, we are going to go ahead and see that the equation is going to be g of x is equal to absolute value. If it is moving to the left, what are we doing to the graph? We are adding, right? So we are going to do x plus how many units to the left? 2. And then after that, we can see it is going down vertically. So therefore, that is minus 5. All right, and so there's my equation, because the vertex is 2 units left of the origin, and then we are going 5 units down from the origin. And so that is why we have this equation. So this is a multiple translation. So next part is the dilations with our absolute value functions. So let's quickly do a quick review of the different forms of vertical and horizontal dilations. So if I have the vertical dilations, it's going to be written like this: A times the absolute value of x. So this is outside, okay, and this is the reason I know that it's going to be vertically dilated. So, and in the other one, in the horizontal, it's going to be inside. So it is paired with the x. All right, so that tells me that this is going to be horizontal. So let's look at this. if a is greater than 1. So let's say this is 5. So think of a graph which is just x and then which is 5x. Okay, so you can easily see that this is going to be a vertical stretch. Okay, this is a vertical stretch because we know that the graph is going up pretty steep. Now, if 0 is less than a and a is less than 1, we know we are talking about a fractional part. So let's say that we have 1/2, or you have 1/4, you have 3/4. These are all fractional parts which are greater than 0, but they are less than 1. So in this case, it's going to be, your graph is going to be more, it's going to be less steep. Okay, so that is why this is a vertical compression. It's going to be a vertical compression. It's being compressed down. So it is flatter compared to how steep the vertical stretch would be. Okay, now let's look at the horizontal one. Okay, if a is greater than 1, now we are doing what? We are performing this function first. So what happens over here? It becomes the reverse of that. And this one becomes a horizontal compression. If a is greater, this is a horizontal compression of the graph. Okay, and so it is the reverse of the vertical. See? And then in this one, if 0 is less than a and a is less than 1, this is going to be a horizontal stretch. So this is going to be a horizontal stretch. So this is the first thing that I wanted you to see, and then we can move on to questions related to this. So once again, multiplying a constant a after evaluating an absolute value function creates a vertical change, either a stretch or compression. And when an input is multiplied by a constant a, before the absolute value is evaluated, a horizontal change occurs. All right, and so I showed you how this is going to be horizontally compressed or stretched. So let's go ahead and do a problem on the whiteboard. And we are going to discuss this dilation. Okay? All right, so let's look at this question. And it's dilations of the form a times absolute value of x when a is greater than 1. And so that's what I was just showing you when we were reviewing dilations. And so describe the dilation in g of x is equal to 5/2 absolute value of x as it relates to the graph of the parent function. So I know that the parent function, my vertex is at 0, 0. That's at the origin, right? Now, let's look at this. If I'm saying 5/2, is that greater than 1? Absolutely, because 5/2 gives me 2.5. So it is definitely greater than 1. So looking at this, the number which is in the front, okay, we know that this is going to be a vertical stretch of the graph of the parent function. So to save us time, I have gone ahead and use the function rule that was just provided to me, and I have gone ahead and created a table so that we can see why it is a vertical stretch. And then I've created the graph. And so once again, we give values to x, and I've said, you know, I'm looking at numbers which are divisible by 2, because it becomes very easy for me to simplify. So I'm going to say x is -4, -2, 0, 2, 4, because I know that those numbers are compatible with 2 and it is easy for me to simplify. So then what is, since, you know, this is multiplied, later. First, what do I need to do? I need to find out the absolute value of -4, and that's going to give me 4. Absolute value of -2 is 2 because that is the distance of a number from 0 on the number line. Absolute value of 0 to 4 is 0 to 4 consecutively. Okay, next we are going to multiply 5 over 2 by the absolute value of x that we just found. And if I divide 5 by 2 times 4, I'm going to get, what is 5 times 4 is 20. And 20 divided by 2 gives me 10. Okay, and then I do 5 times 2 is 10, divided by 2 gives me 5. And then 5 times 0 is 0, and of course that's going to stay a 0, divided by 2. Okay, and then I have 5 times 2, so same thing, the 2 and 4 is going to give me the same result because it's absolute value. Okay, and so now my new ordered pairs are -410, -25, 0, 0, 25, and 410. So when I take these values and I put it into the graph, look, this graph has become way steeper than the original parent function graph. And so that is why this is a vertical stretch of the parent function. Okay, so this is a vertical stretch. So 5 over 2 absolute value of x is a vertical stretch of the graph of the parent function. Now let's do another one. And again, I am going ahead creating tables and graphs from before just to save us time, because by now you know how to create that table and to create the graph. All right, so let's look at this question. And now this is in the form where it is absolute value of ax, and so that I can already see in my head that's a horizontal dilation. So depends on if the value of the a is going to be greater than 1 or whether it is going to be 0 is going to be less than this or than a, and a is going to be less than 1. So depends on which of those I'm using. So in this case, clearly, look, describe the dilation in p of x is equal to absolute value of 2x as it relates to the graph of the parent function. So when I'm looking at 2, is 2 greater than 1? Absolutely. So since 2 is greater than 1, I know that this is going to be a horizontal compression. Okay, so let's go ahead, and I have already created the table and the graph so that you can look at this. And here we go. So for p of x is equal to 2x, a is equal to 2. All right, now we know that a inside the absolute value symbols, the input is first multiplied by a, right? So then the absolute value of ax is evaluated. So we are doing that, we are plotting the points after that. So, but let's put it in the table. So we have -4, -2, 0, 2, 4. Again, I'm taking those same values. And now we are going to first do what's within your absolute value symbol. So we are multiplying the 2 with each of those numbers inside first. So we have 2 times -4, that gives me -8. 2 times, so this is all with absolute value. Okay, 2 times -2 gives me -4. So this is 0, this is 4, this is 8. And then we find out the absolute values of each of them, and I get 8, 4, 0, 4, 8. And therefore, my ordered pair is -4, 8, -2, 4, 0, 0, 2, 4, 4, and 8. And I am going to put this into the graph, which is here. And you can see that p of x is equal to absolute value of 2x. It is a horizontal compression of the graph of the parent function. Okay, so that is a horizontal compression. So let's look at these three that I've written in red really quick and do a quick refresher on the type of dilation that we have here. We are going to identify the dilations. So let's look at the first one. So we can see g of x is equal to 3 absolute value of x. So this is on the outside, right? So this is going to be vertical. And because it is greater than 1, this one is a vertical stretch. This is a vertical stretch. Okay? Let's look at the second one. What is this one going to be? Is it greater than 1? No. Is it greater than 0? Yes. So what is this one going to be? This is a vertical compression. This is a vertical compression. Same thing with this one. That's also a vertical compression. Now, what about if I had done this? If I had taken this and I had done 1/3 x. Okay, so what do I see now? So now we have to solve for everything which is within the absolute value symbol first. Okay, so this would make it what? This would make it horizontal. And since again, this is my greater than 0, but less than 1 because it's 1/3, this would be a horizontal stretch. This would be a horizontal stretch. Okay, so this is something I just wanted to show you before we moved on to reflections. But let me go ahead and show you some more examples. All right, so let's look at these really quick. Just to refresh, it's saying match each description of the dilation with its equation. So the first one, it's saying stretched vertically. That means that graph has to be steeper. So if it's in the format of AX, this A has to be greater than 1. So let's see which one relates to this one. No, this is inside, this is inside. So these are horizontal. These two are vertical because they are on the outside. Now, since it has to be greater than 1 for stretched vertically, here is my answer. P of x is equal to 6 of x. Okay? And then if I'm talking about compressed vertically, it has got to be, in this one, it has got to be where a is greater than 0 but less than 1. So it has to be a fractional part multiplied with the absolute value of x. So if I'm looking at that, this is the one where it is compressed vertically. All right? Now, when it says it has to be stretched horizontally, remember that it's the reverse of this. So in stretched horizontally, the A has to be greater than what? If it's stretched horizontally, it is definitely going to be a value which is a fractional part because it's greater than, A is greater than 0 but less than 1. So if I'm looking at stretched horizontally, it is going to be this one. And then in this one, since it's horizontal, A has to be greater than 1. And is 4/3 greater than 1? Yes, because 3/3 is 1. So 4/3 is greater than 1. So this one is compressed horizontally. So this is what I had wanted you all to see. And so we had just talked about this, but I wanted to give you a visual of this with the table and the graph already created. And now we're talking about a dilation over here when 0 is less than A, less than 1. So once again, since we are describing this dilation, J of x is equal to 1/3 absolute value of x. Now once again, since the A is on the outside, I know that this is going to be a vertical dilation. And once again, since the number 1/3 is greater than 0, but it is less than 1, this is going to be a vertical compression. Okay, stretch is when it is greater than 1. So if this was 4, 5, then that would be a stretch. But a compression is when it's a fractional part. So that this graph, in a stretch, it goes steeper. In a compression, it flattens. So this graph is going to be flatter. So let's look at, I'm going to just help you create the table really quick, and then we can look at the graph and what I mean by it becomes flatter. Okay, it's a compression, it's compressed. So here we go. Here is my table that we have created, and for j of x is equal to 1/3 absolute value of x, a is 1/3. And because it's outside the absolute value sign, the absolute value of the input is first evaluated before I can multiply by a. Okay, so absolute value of -6 is 6 and -3, 3, 0, 0, 3. So that's the first thing. So I've just given certain values, and the reason I've taken -6, -3, 0, 3, 6, these values, because if I'm looking at 1/3, I'm looking at numbers that are compatible with my denominator to put in the numerator, so I can simplify. So that would be 3, 6, 9, 12, that is multiples of 3, right? So that is why I've taken -6, -3, 0, 3, 6, okay? So now once I've found the absolute value of x by giving those values, now next I'm going to do 1/3 times this. So 1/3 times 6 gives me 2, 1/3 times 3 gives me 1, 1/3 times 0 gives me 0, 1/3 times 3, 1, 1/3 times 6 gives me 2. So now here are my new values of j of x over here, x and j of x, and that's -6, 2, -3, 1, 0, 0, 3, 1, 6, 2. So now once I have these ordered pairs, I'm going to take them all and put it straight into the graph. And here is my graph, look, compared to the parent function. And you can see that 1/3 of x is a vertical compression of the graph of the parent function. See, it's compressed more, it is more flat compared to being steeper or stretched when we have a value which is greater than 1. But in this case, it's a fractional part because greater than 0 but less than 1, so the graph is flatter. So now we're getting into reflections, and just let's do a quick recap of reflections. So if I have g of x is equal to -a absolute value of x, this is, as we can see, we had talked about this. If it's written like this, my x is going to go over the x-axis. X stays the same and the sign of y switches, right? So we can see in this case that my graph is going to reflect over the x-axis, okay? So this one is reflecting over the x-axis. And I also need to realize that when I have a graph like this, it's going to be flipped upside down compared to a of x. Okay, so in this case, what I mean by it's going to be flipped upside down, they are definitely symmetric about the x-axis. So I know that in the parent function of the graph, let's say this was my graph over here, and here is my parent function of absolute value. And so when I'm saying it's going over the x-axis, what I mean is that it is being flipped like this. Here, it becomes upside down. And that's what this graph means when it's going over the x-axis. Let's look at the other one. This is now grouped inside. Okay, so this is, now we know that outside there's nothing, okay, so we can say this is 1, times this. All right, so therefore the x now, okay, y is going to stay the same and the sign of x is going to switch. So what does that happen? We are going this way. And when I'm going from left to right, what is this? We are flipping, or we are reflecting over the y-axis. We are reflecting over the y-axis. Okay, so now let's look at some examples over here really quick to see what kind of a reflection it is, and then we can go on to some problems. Okay, so let's look at this one. G of x is equal to negative 6x. So I know that my x is going to be the same. That means it's reflecting over the x-axis, and it is going to be, see, I have what, negative 6 on the outside. So this is a vertical stretch, okay, and reflection over the x-axis. So reflection over the x-axis. Let's look at the next one. Since it's inside, we know that this is a horizontal stretch. This is a horizontal stretch, and reflection over here, since this is negative, inside we know that y is going to be the same. So this is reflection over the y-axis. And then the last one, where I have g of x is equal to negative 2x, absolute value of negative 2x, I know that this is going to be a horizontal compression, and it is reflected over the y-axis, reflected over the y-axis. So I just wanted you to get a quick refresher of this, and then now we are going to move on to do some problems on the board. All right, so let's look at this problem, and it's saying describe how the graph of j of x is equal to negative x plus 3 plus absolute value plus 5 is related to the graph of the parent function. So we know that the graph of the parent function is f of x is equal to absolute value of x. And this is the graph of the parent function. Now, I need to also remember from what I said in the beginning. When I am looking at the vertex, that is this point, okay? Now, if I look at the equation, what is the vertex for the parent function? This is 0 and this is 0, and that is why we have 0, 0. Okay, now let's look at what the vertex is going to be. Okay, so since we are looking at this one, and I know that my x and my y, so we can see that the negative is outside. That means it's going to be reflecting over the x-axis. Okay, and then I know that when the graph is saying plus, which direction is it shifting? To the left. So therefore, if I look at my vertex, which is ordered pair is H and K. Okay, so if I'm saying x plus 3, that means that we are shifting to the left, and so therefore my H is going to be negative 3, and what is K? K is here, is 5. So this is where my vertex is going to go off the graph, and since we are reflecting on the x-axis, my V is going to flip. Okay, so let's go ahead and I am going to graph this with black. So I said negative 3, 5. So that means it has shifted 3 units to the left and it has gone up 5 units because plus 5. So this is my vertex of my graph. Okay, so this is my vertex, and so I can see over here h is what? This is negative 3 and 5. Okay, and then after that all I'm doing is I'm taking this graph and I am just flipping it. Okay, so it's going to go like this. And there is my graph, and I can see that it has gone 3 units left and 5 units up. Now, let me show you, even if I didn't do it just based on this, if I had created a table and then gone ahead and done this, let me show you, it's going to end up with exactly the same thing if you choose to give values to x and then evaluate and do it. Okay, so here you go. So here we go, same thing. You create the table first. You've given your values to x, negative 5, negative 4, negative 3, negative 2, negative 1. We are going to evaluate everything within the absolute value of x plus 3 first. And so negative 5 plus 3, negative 4 plus 3, negative 3 plus 3. So we get these values, negative absolute value of negative 2, negative 1, 0, 1, 2. And then of course we give the absolute values is a positive value. And then we have the negative outside. So all of them become negative. And then we are doing our negative 2. And then we have going to add that to the plus 5, which was the constant outside, telling us that it is vertically moving up. So there we go. These are the new values. And then I have my ordered pair. So to save us time, I'm just showing you based on the graph. Even if you form a table, you are going to end up with exactly the same answer that I just showed you. So look, this is in 2, 4, 6, 8. That's how the intervals are. But literally I took the parent function and I moved it. As you can see, it said x plus 3, so we're going in the opposite. So I moved it 3 units to the left, and then I moved it, said plus 5, 5 units up. And then I have, of course, because it's a reflection on the x-axis, the entire graph gets flipped upside down, and that's what this is. Okay? So here's another example, and now it's talking about a value which is greater than 0 but less than 1. Once again, the negative 3/4 of the absolute value of x is written in the format over here. So I know that this is again going to be a vertical dilation, and since it's a number which is greater than 0 but less than 1, this is going to be a graph which is compressed. And now we can see that my x value, because inside, see, there's no negative inside, that is going to stay the same, and the y value is going to flip, that is the sign. So this means the graph is being reflected across the x-axis again. And since it's reflected across the x-axis, we know that it's going to be, instead of this, it's going to be this way. But we can again go ahead and start giving those values in the table to x in order to calculate. And for me to see that I have negative 3/4, so I want to take numbers which are compatible with my denominator, that is 4. So I want to use 4, 8, 12, 16, 20, etc. These kind of numbers that I can just simplify when I am dividing the numerator by the denominator. So there you go. I've given those values. We're going to find just the absolute value first of each of those. And then look, 84048. Then I'm going to multiply negative 3/4 with this. And so I end up with these answers. And here I have my ordered pairs. So once again, I've created the tables for you in order to save us time. And now let's look at what the graph looks like. There we go. So again, upside down version. And then we do have 0, 0. But again, the graph is not as steep. It is more gentle like this. So it is more compressed. And so that is why this is the graph of the parent function reflected across the x-axis and vertically compressed. So let's look at this one now. Now it's in the format of y is equal to absolute value of negative ax. So looking at that, I already know that's horizontal. Okay, so depending on the value of a, we'll see whether it's compressed or stretched. So describe how the graph of g of x is equal to absolute value of negative 4x is related to the graph of the parent function. So when I'm looking at this, I know that my a is greater than 1. So in this case, it's going to be horizontally compressed in relation to the parent function. So I'm just going to show you the graph. Here you go. This is the parent function. You are welcome to put your values into a table and format, but when you do here is a horizontal compression of that graph. All right, so now we are going to go ahead and we are given a graph, and we are given a function of the absolute value, and then we are supposed to graph it. So I've gone ahead and again created the graph of the parent function. f of x is equal to absolute value of x. And so I know that 0, 0, 1, 1, absolute value of, so these are going to be in the same thing. So it's a piecewise defined graph over here, a function. And so let's go ahead, and I've given you this value where I have g of x is equal to absolute value of x plus 1 minus 4. This gives me horizontal shift, and this gives me my vertical shift, my vertical movement. Okay, so as I can see with my x plus 1, that means the graph is going to go 1 to the left and is going to go 4 units down. So when I'm looking at this, please remember my vertex, okay, is going to be opposite of what is a 1, because you're going in the other direction. So my vertex is going to be negative 1, and then I have negative 4, okay, which is my y, and that's where I am going to be plotting this. So once again, I am going to move, as I said, x plus 1, so I go 1 to the left, and then I say minus 4, so I am going 1, 2, 3, 4 down. Okay, so there is no reflection going on over here, and so therefore what I do in this is I have my rise over run is just going to be 1 and 1. Okay, so I have 1, and this is supposed to be negative 1. So yeah, so 1 and 1, 1 and 1, and so I can see it's the same graph. Okay, and then I have this, and we have same thing here, and we have again this way and this way and this way. So okay, here we go. All right, so this is how my graph is going. And I can see that in this case, what has happened? It has shifted 1 to the left, and it has gone down 4. And you can see that the graph is translated 4 units down from the parent function. And so in the graph of g of x is equal to absolute value of x plus 1 minus 4. It's the graph of the parent function translated 1 unit left and 4 units down. Okay, and so if you see, the domain is all real numbers. Okay, so my domain is all real numbers, and my range, okay, for range you look at the lowest point. Okay, and what is my lowest point in the vertex? It's -4. So the range is all real numbers greater than or equal to -4. Okay, so all real numbers greater than or equal to -4, because as you can see, that is the lowest point of the vertex. Okay, so this is how I graph this one. Let's try another problem. So now let's look at the next problem, and let's say I say g of x is equal to, now negative sign on the outside, x minus 7 minus 3. X minus 7, absolute value of x minus 7 minus 3. So since I can see this, I can already see that with that negative sign outside, it's going to be a reflection on the x-axis. That means my graph is going to turn upside down. My v is going to turn upside down. So let's first identify what the vertex will be. Okay, so if I say the vertex, we know that the vertex is, this is x and this is y, right? So I know that if it's x minus 7, I am going horizontally how much? It's to the right. So therefore, my vertex is going to be 7 units, which is x, okay? And then I have, this is going down, so this is my y. So minus -3. So 7, -3. And that is where my vertex is going to be. So if I was taking this graph, all right, and I know that I'm shifting 7 units to the right from here, 1, 2, 3, 4, 5, 6, 7 units, and this is a horizontal shift, and then we are translating vertically, and so 7 and then 1, 2, 3. So this part here is the vertex of my absolute value function of the parent function is being shifted that much. And so then I'm looking at, okay, if this is negative, this means what? This means -1. This means -1. Okay, I don't know if you can see that color. So this means -1. So of course I am flipping my graph, and so this means, what does this mean? This means that my rise over run, that means it's -1 down, okay, and 1 right, because this is rise over run, right? Rise over run, talking about the slope of my graph. So when I go ahead and plot this, it's going to end up looking something like this. Okay, so it's going to look upside down like this when I'm plotting. So we have here, we have our rise and our run, and our rise and our run, and rise and run. That's what I mean. 1, 1, 1, 1. Okay, and this is what my graph is going to end up looking like. So let's look at the domain. The domain is all real numbers. All real numbers. Okay, and then let's look at the range, and I can see that I need to look at what is the highest point over here. So my highest point is what? It is 3. So therefore my range is y is less than equal to what? To negative 3. So everything less than that is going to be the range, which is the output. Okay, so here's another example. G of x is equal to negative 2 absolute value of x minus 1 plus 5. So looking at this, I can automatically see that it's going to be a reflection on the x-axis. And if it is saying x minus 1, that means I am moving to the right. So I'm looking at what would my vertex be for my absolute value graph. Okay, so if I have my vertex, okay, so I know that if it's saying moving, it's x minus 1, that means it's moving to the right. So this is 1 and this is 5. That's where my vertex is going to be. All right, once again, this is x, this is y for my ordered pair for the vertex. Okay, so then I'm looking at, okay, it is saying negative 2. So that is telling me if I'm looking at my rise over run, okay, if I'm looking at rise over run, it is going to be negative 2 down. So we are doing down 2, okay, so down 2. And how much on the right? We are doing right 1. Okay, so down 2, right 1. That's what this means. And so let's go ahead and plot this. And my ordered pair is 1, 5. Okay, so this goes here, which is 1, 5. Okay, and so then it's saying I am going down 2. So that's what this means. So this goes 1, 2, 1, 1, 2, 1. So in this pattern, okay, and then I just take this and I do this. And same thing, the reflection on the other side. Same thing, and then we are going here. 1, 2, 1, and then 1, 2, and 1. So here, there we go. And then of course we do this. So that's just how to graph it based on the function rule that is provided to me for absolute values, and just know where to find the vertex and look at whether it's a reflection or not. If it's a reflection, my vertex, my graph is going to become an upside down V in this of the parent function. Okay, and then of course we are translating it based on whether it's a horizontal shift or it's a vertical shift going up or down. All right, and so that is how I have created this graph. So the last two examples, I'm just going to go ahead and show you on the board really quick because here we are graphing j of x is equal to absolute value of 3x minus 6. And the absolute value of that, we're stating the domain and range. So looking at this, I know it's inside, so it is going to be a horizontal transformation. So let's quickly use a table to solve this. And with the graph of j of x is equal to 3x minus 6, okay, and we get our values as 0, 6, 1, 3, 2, 0, 3, 3, 4, 6 when we are solving it. And then as when we graph it, look, because A is inside the absolute value symbols, the effect of H on the translation changes. And this is how we are going to evaluate the function for several values of x, and that's what we had created the table for. And so as you can see over here, what happened? This is definitely a horizontally compressed graph, okay? It's translated 2 units to the right, because here we go. See, it's translated 2 units to the right and it is horizontally compressed, okay? And then let's look at what is the Domain is all real numbers always, and range is all real numbers greater than or equal to 0. You always look at the bottom point of your the vertex, and then based on that we are calculating. The range is the one that is mostly affected. Domain is always the real numbers, and then range is we are looking at where it is. So everything greater than equal to 0. Okay, and here's one last one. Just look at this really quick. And we know that in this one, what's going to happen? It is going to be, just looking at this, I know it's going to be a reflection on the x-axis. And if I'm saying x minus 3, that means my graph is moving 3 units to the right. So what is my vertex? Is going to be 3, 5, because then it's moving 5 units up. And so based on what I just showed you, once again, my vertex is going to be H and K, and so if it's minus 3, it is moving to the right. So now my vertex is going to be 3 and 5. So really quick, here it is. So look, 1, 2, 3, and then 1, 2, 3, 4, 5. There's my vertex, and since it was negative, that means my is reflecting on the x-axis, and then it just, the graph just flips. It becomes an it is become an upside down V like this, and it's moved up over here. Okay, and then of course one down and then one right, one down, one right, and that is how we are doing the slope over here. And so once again, negative x minus 3 absolute value plus 5, the parent function is reflected across the x-axis because the absolute value is being multiplied by -1, and then the function is translated 3 units to the right. So this is a quick refresher of what we have done, and then of course the function is translated 5 units up. And so yeah, this lesson was pretty intense, but it is a review of everything we have done. And we have looked at, of course, how to find the vertex when we are graphing. And please remember, once again, in the formula that we have over here, A is the absolute value of x minus h plus k, where a, h, and k we know are the constants. And please remember that when we are trying to find the vertex of the new graph, my h is always x and my k is the y. Now, if it is minus, we know the graph is shifting to the right, so that x is going to become plus. If it is plus, we know it's going to move to the left, and so my x is going to become negative in the ordered pair. Okay, and then of course my constant k, that is the y value when we are solving for these functions. Okay, and now that completes our module 4. Woo, that's a big one. So linear and nonlinear functions, that's what module 4 is about, and this was our last lesson for this unit. Have a fantastic day, everyone.